Welcome to the next video. So again, we have now looked at 5 main or basic rules that help us to plot the root locus, and this talks about the total number of branches being equal to the number of open loop poles or zeros, whichever is greater. We have also looked at symmetry, where we said that the root locus is always symmetrical about the real axis. We have also looked at the beginning and the ending point for the root locus, where we said that it begins on an open loop pole and ends on an open loop 0. We've also looked at the behavior at infinity, where we said that they start and end at infinity. They start or end at infinity along asymptote, okay, lines of asymptote. And these lines, we know how to compute the centroid, or the point where it touches the real axis, and then we know the angle, that's the angle from the real axis. We also talk about the allocation on the real axis and said the root locus for k greater than or equal to 0, the root locus is going to lie to the left of an odd number of poles or zeros combined, okay. And we stated that that is where it will be located, and that helps us to plot the root locus on the real axis. These basic rules help us to plot it, but there are some important points we will need to also find. For example, okay, so we are going to look at refining the sketch. So how do you refine the root locus sketch? Okay, so there are very important points we need on the root locus to help us in our computations, and we are going to look at some of them in this lecture, and the subsequent lecture will also look at another one, okay. So first, for example, if I have a pole here and a pole here, a 0 here and a 0 here, then as we said, the root locus will originate from the pole, okay. So of course it will lie to the left of an odd number. This is 1, 2, 3, and 4. So the root locus will lie here, and then the other one will lie here, okay. So you will see that in terms of origin, it will originate from here, and here there will be another one ending on this 0, another ending on this 0. So immediately it makes sense to say when they crash here, they will depart, and then they will come and land here. Then this one will also depart, come and land there, okay. One will branch here and one will branch to the left, okay. So this will be the root locus. Now the very point where they depart from the real axis here, we call it the breakaway point. Okay, and the very point where they arrive here, we call it the break-in point. We don't know these 2 points, and so we need to find a way to calculate the breakaway and the break-in point, okay. So this system here, I can easily, so if I give you the root locus of this like this, and I say plot, find the KGH, you should be able to find it. That is K. So let me label this as 1, 2, 3, 4, okay, and -1, -2, -3, -4. You should be able to find this easily as S -2, S -4, all over S plus 2, S plus 4, okay. So this is the KGH, and of course you can find your T of S also to be equal to, so your T of S is going to be what? T of S is going to be K G H over 1 plus K G H. And that is going to give you that K S minus 2, S minus 4, all over S plus 2, S plus 4, all over 1 plus K S minus 2, S minus 4, all over S plus 2, S plus 4. Okay, so this will be your K, your T of S, which of course is the same as K S minus 2, S minus 4, all over S minus S plus 2, S plus 4, plus K into S minus 2, S minus 4. Okay, so this is basically what we are going to have for our closed loop transfer function, and we are looking at the poles of this as, or the roots of this characteristic equation formed from the denominator polynomial as k changes, and that's the root locus. Anyway, so if this is the case, obviously we can easily go down and look at it. Of course, we have already done the plotting here, and we see that there is a breakaway and breaking point. So how do you compute this breakaway and breaking points? Well, there are 3 methods for doing that. Okay, there are 3 methods, so we'll look at them. But before that, let's look at how the behavior is. Okay, so you'll see that here we have k equals 0. It will come till k equals a certain value. Let me call it x. At this k equals x, okay, then you see that it will depart from the complex axis. Okay, so that means that k starting from 0 to k equals this x, it departed from the complex axis. Then that tells me this is the maximum, okay, k, for which the roots s equals real number. Okay, so this is the maximum k for which the pole is going to be real number. The same way, you see that it lands here, okay, and then it moves towards the zeros. Okay, it lands with a value k equals y, and it moves to 0 at k equals infinity. Okay, so what can I say again? Well, it means this then will be a minimum value for which it lies on this complex number. Okay, so this k equals y is a minimum value. Okay, so k, so for which s equals real number, okay, when it comes to this session. So this tells us that in order to find k, we will need to find some, should I call it, turning point or optimal point, or a minima and a maxima. Okay, okay, so, or optima as we usually form it. So how do we find that? Well, so anytime you want to solve for it, there are 3 methods. Okay, okay, one of them is an algorithm method where you program it in a computer. So I'm going to take that out and deal with 2 other methods. Okay, since this is a so the method number 1, since it's a maximization or minimization problem, as an engineer, anytime you hear maximization or minimization, yeah, you know that you are going to have to differentiate. So in that case, you have to find k, because the value of s on the real axis for which k is maximum or minimum. So I can find k in terms of s. Okay, so k as a function of s, and then I'll find the k, the s, and evaluate it at s equals a real number. Okay, and then whatever I will get, I will equate that to 0. The values of the real number that gives me the 0 then becomes my point of breakaway point and break-in points. Okay. So again, let me go through it. So first, we are going to differentiate our k with respect to s. Okay, we are going to substitute s equals real number, and then we are going to equate that to 0 to find the maximum and minimum points, and that will give us the point of arrival and departure. Of course, the same expression will give us maybe 2 values or 3 values or 1 value or whichever, okay, number of values. And so when we get the values based on the root locus plot, we'll then be able to determine which one is a break-in point, which one is a break away point, and that can be deduced from it. So let's look at, for example, the system we have up there. Okay, so we said that our k gh equals, okay, from actually 1 plus k gh should be equal to 0. Okay, that is what we said the root locus originates from. And therefore, our k gh equals minus 1. Okay, and so our k equals minus 1 over gh. Okay, so for example, the system that we have been given up there, our k gh was given to be k into s minus 3, s minus 5 all over, so this system actually this, I have calibrated it wrongly here, but for consistency's sake, okay, so minus 4. Okay, let me just forget about that one and draw a new one. Okay, so let's say we have been given a system like this: s plus 1, s plus 2, oh no, yeah, okay. So if we plot the root locus for this, we are going to get 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Minus 1, minus 2, minus 3, minus 4, minus 5. So this is what we have, and this is the j omega axis. So if you plot this, the zeros will be 3 and 5. The poles will be minus 1, minus 2. So we are going to have our poles minus 1, minus 2, and our zeros 3 and 5. Okay, and so the root locus will just be here and there, and this will be departure, this will be arrivals, and it will depart from here, arrive here. Okay, so that will be the way it will look like. So how do we find the break away point and then the break in points here? Okay, so we solve it by writing the expression. So we have our k equals minus 1 divided by s minus 3, s minus 5 times s plus 1, s plus 2. Okay, so this is going to be our expression. Okay, therefore our dk of s over ds will be equal to it's going to be equal to 11s squared minus 26s minus 61 all over s squared minus 8s plus 15 all squared. So you can use the quotient rule to do this. Okay, and so we'll take the k of s, the s evaluated at s equals sigma, real number, will be equal to 11 sigma squared minus 26 sigma minus 61 all over sigma squared minus 8 sigma plus 15 all squared. So what we have to do then is to equate this to 0, and that will give us 11 sigma squared minus 26 sigma minus 61 equals 0. So to find the values, solve for sigma. Okay, and when you solve it, you will get sigma equals minus 1.45 and sigma equals 3.82. So let's come to the plot. And which one is going to be a breakaway point? Of course, you see that the breakaway point is between -1 and -2. Therefore, breakaway point equals minus 1.45, and then the breaking point is going to be equal to, if you come here, you see the breaking point is between 3 and 5, and so that is going to be equal to 3.82. Obviously, after solving, if my breakaway point was outside the range -2 and -1, immediately I would have known that I made a computational mistake. And if my break-in point was outside the range 3 and 5, I would know that I made a computational mistake. So what I'm trying to say is that when you solve it and you are not getting any value in the ranges that you need, then obviously you know you have made a mistake. These are refining of components, so it should immediately tell you that it does not violate the sketch. It only tells you a specific point on the sketch. Okay. So again, that is how to compute the breakaway and breaking point. That is one of the methods. But I'm sure some of you don't like this whole differentiation issue. So if you don't like the differentiation but you love algebra, then you can use the second method, okay, which says the breakaway and breaking points satisfy, okay, the relationship, okay, summation from I equals 1 to m of 1 over sigma plus zi, okay, where zi are the negative of the zeros, should be equal to, okay, summation j equals 1 to n 1 over sigma plus pi's, where pi's are the negative of the poles. Okay, so if you don't like differentiation but you like algebra, you are okay with this one. So you just find all the poles, all the zeros, and negate them and plug them in here. So these are actually the sum of the factors, okay, of the reciprocal of the factors of the numerator polynomial is equal to the sum of the factors of the sum of the reciprocal of the factors of the denominator polynomial. Okay, so that's what this is saying. is saying the sum of the reciprocal of the factors of the numerator polynomial okay, that is the open loop of k in h is equal to the sum of the reciprocal of the factors of the denominator polynomial. Of the KGH, the open loop transfer function. So this is something that you should know. And once you plug in your values, you are going to get your answer. Okay. So in the one we have above, you are going to get 1 over. So the first factor is the polynomial was given by this. So the numerator polynomial, the factors are s minus 3 and s minus 5. So you get 1 over minus 3 plus 1 over sigma minus 5 equals, okay, the sum of the factors of the denominator polynomial, and that is going to give us s plus 2, s plus 4. So that is going to give us 1 over sigma plus 2 plus 1 over sigma plus 4. Okay, so now you are going to solve this equation, and when you solve it, you are going to get, so after solving this, you will come to actually the same equation like we had here. Okay, you come to this same equation, copy. So this will evaluate to this equation, and then you can solve this equation to find your sigma 1 and sigma 2. Okay, so this again is something that you can easily do. Okay, of course, like I said, the third method is using algorithm or computers. Okay. This second method, actually, you can derive it yourself by using the differentiation and doing some manipulations to that, and that will bring it. So here, actually, what they have done is they have already done the differentiation for you so that you don't have to go there and worry yourself. Okay. So that will bring us to the end of how to compute the break-in and breakaway points. Okay. Next, we'll look at how to compute the J omega crossing. So computing the significance. What is the significance? Of break-in and breakaway points. Okay. So for at least for the second order system, okay, this tells us where, so it tells us the transition, okay, transition from real roots to complex roots. And that's to say transition from overdamp to underdamped. Okay, of course, through critically damped point. Okay, so that is what. So with this, we'll be able to find the value of K, the range of values of K, or the gain for which the system is underdamped, and the range of values of K or the gain for which the system is overdamped, and the exact value of K at which the system is critically damped. We'll be able to find that by using or by computing the breakaway points. Okay.